Hi, everyone. So my name's Nick and I'm a fusion scientist. I've been working in the field for about a decade now. And as Chris said, I don't profess to know everything about everything, but we can certainly give a good stab at most of the questions that you've got for us. And as the format suggests, you're free to ask us anything. We might have to refer you to Dr. Google or Professor Wikipedia if we can't answer things ourselves, but we'll have a go. I see Chris has got the screen sharing going. So as Chris said, please put any questions you've got in the Q&A chat at the bottom of the screen. And after Chris has given you a quick introduction, which hopefully will spur on your questioning and inquisitive minds, I will go through a few of the questions that we've had pre-submitted and give you a bit of time to think up any burning questions that you'd wish to ask us. So I will hand over to Chris. Chris, your slides are on the, I think, presenter view rather than the full screen view.
Yeah, and I can never work out how to do that. So see your slides. Hide presenter view. How's that? Is that better?
That's perfect, yeah.
Hopefully that's better. Good. Okay, so very, very quickly, we figured it would just be worth talking a little bit about fusion. Trying to describe fusion in 4 slides is incredibly hard to do, but that's what I've endeavored to do. And first of all, it's why we do it, because a lot of the rest of the questions will be on some of the challenges that we have faced and continue to face. So it's worth reminding ourselves that this is could really be transformative in the way of making electricity in the future. So why do we do it? Low carbon, you're not burning fossil fuels, you're not releasing carbon to the atmosphere. This is a really live issue at the minute and worth just spending a little bit more than a line or two on. In the strictest sense of the word, fusion produces no radioactive waste, in the sense that its byproduct is helium, which you would continue to use within the plant. So your waste stream is something that is completely non-radioactive. However, there are 2 routes to which activation does occur in a fusion power plant. One of your fuels is radioactive tritium. That's the fuels we intend our first power stations, at least, excuse me, to start with. And that has a relatively short decay time of about 10 years. So half disappears in 10 years. So it won't leave you with a long-term legacy, but that inevitably gets embedded into some of the surfaces of the structure of the machine. So you end up with a structural activation. The more difficult one is the very fast nucleus that fusion produces also affect the materials. It can damage the materials. It's going to pummel out into the structural materials, and indeed you're going to slow it down to turn that energy from the neutron into heat and then electricity. But how it interacts with the materials depends on what materials you choose, and you will activate parts of standard stainless steel, standard structural materials, and what they're made of will define how long that activation lasts. So for instance, cobalt 59 in stainless steel will turn into cobalt 60. Therefore, you will have a mixture in your structural materials, depending on what structural materials are, of activations. And that might last up to a few hundred years, maybe even 1,000 years. Worth bearing in mind, that's still significantly shorter than fission. It's within the plant rather than being produced as a product that needs to be taken away. So there are particular advantages, and we are working really hard to find materials that minimize that down. So apologies that took a little while, but it's quite a live issue at the minute. This is much less live. Fusion is frankly so hard to do that it will always stop itself. It is incredibly hard to get the conditions right, and I see some of the pre-assigned questions already are discussing that issue. You cannot have an internally driven accident, because frankly, whatever happens that you do wrong, you overfuel, you underfuel, underheat, overheat, your plasma, it will always find a way of stopping itself. So it's very tenuous to get going, therefore easy to stop. And the fuels are really abundant: deuterium and tritium. Tritium available from breeding in a future power plant from lithium, one of the more common elements in the Earth's crust, and deuterium, 1 in 6,000 to 7,000 water molecules is deuterium. That doesn't sound like much, but there's an awful lot of water, and certainly the rate at which we would use deuterium, you potentially got millions of years worth of supply. So a fantastically effective way, mid-century, of producing low carbon energy, and really an option alongside renewables and advanced fission. For those, and most of you do, of course, what is the best analogy we can use? We are doing essentially or similar to what the sun does and all the stars. So in a galactic sense, fusion is a very common process. Here on Earth, it's very, very uncommon. And you are trying to essentially make a miniature sun. Where we diverge from that is to use these two heavy isotopes of hydrogen I've already talked about, deuterium and tritium, stuck together to make helium and the nucleus. That's the reaction we want to get going. Why? Because in fusion land, that's a relatively easy one to get going. In the sun, hydrogen and hydrogen is sticking together at a lower temperature, I will admit, than the one that we wish to get going. In the sun, about 15 million degrees required for fusion to occur. For deuterium tritium, about 150 million degrees. But the sun and pretty much every star out there doing hydrogen fusion, incredibly inefficient process, very, very ponderous, and no way we could recreate it to produce any meaningful amounts of electricity here on Earth. So we have to choose a better reaction. And deuterium and tritium is the easiest one, in inverted commas, to get going. But that is essentially what you are trying to do. If you remember nothing else from this, it's trying to put a sun inside a bottle and make electricity from it. Why hard then? Because fusion doesn't happen easily. Fusion is a very difficult process to get going. The conditions required, as I've already mentioned, are very difficult. 15 million degrees temperature in the sun. That just means that my nuclei are moving fast enough to overcome the fact they're both positive and stick together and create this fusion process. In the case of deuterium tritium, 150 million degrees C, about 10 times hotter than the sun, as I said before. Deuterium, more like 400 million degrees C, proton boron, hydrogen boron, around 1 billion degrees C. So again, deuterium tritium, one of the easier reactions to get going, but we have to get and hold and sustain a plasma inside a device and heat it up to 10 times hotter than the sun. So instantly you can see some of the challenges we face. We need to get it as dense as we possibly can, and there's hard limits there, as hot as we can. And we need to keep it as well confined as possible. A plasma is ever so good at losing its heat and energy out. And the way we do that at the minute, or one of the crude ways we do that, is to increase the size of the devices to increase the insulation, if you will, of the core of the plasma. But if you contrast this with fission, then you see it is a very, very different process with very different science and engineering involved. A little bit on just where we're going. Many of you will know we operate Europe's fusion experiment jet, and have done for many years and indeed decades at Culham, the largest and most powerful fusion experiment in the world. These are tokamaks, so-called magnetic devices that use powerful magnetic fields to hold the plasma in place. And we also have just upgraded our more spherical and compact device, MAST, the mega amp spherical tokamak, now incredibly effectively called the MAST upgrade, because it's been upgraded. It's just started running in the last few months. And we're very excited about how that routes through to potentially smaller and more compact fusion power plant designs. We are very involved, therefore, in a UK stream, but we're very involved internationally as well. An international next step device from JET, a machine called ITER, will produce you 10 times more power out than in for an hour or two at a time, and test the engineering all together in one device required. So it's genuinely, looking at validating all the engineering for the first power stations. And then there are a number of power plant designs beyond that. In the UK, we're looking hard at a more compact device, like a larger MAST upgrade, if you will, called STEP, spherical tokamak for energy production. Europe is looking at a demonstrator called DEMO. China is looking very hard at a machine called CFETR, the Chinese Fusion Energy Test Reactor. And as you move up towards ITER and beyond to power plants, some of the big challenges don't become, bizarrely, heating a fuel 10 times hotter than the sun. They become, what do you need to make the machine out of? How can you maintain it? And we are building and have built a number of technology facilities to work with partners, industry, academia, etc., looking into all these major areas. So just a name check along the bottom, a robotics maintenance center called RACE, a materials research facility, MRF, and we've got new centers coming along looking in particular at tritium and how you can join and test and validate fusion components specifically for this exciting new field of research at the minute and technology, but one day for energy production. So we're very much forward looking at UKA in that regard. And that is me. I'm going to stop sharing and we'll kick off with some questions.
Great, thanks, Chris. I'll give you a break for a minute, and I'll take a couple of the questions that we had pre-submitted to us. Hopefully that was a really interesting introduction. Hopefully that's given you all a bit of time to think up some more questions. I can see them coming in the chat already. So the first questions I'm going to go through are a bit about my personal background is in physics and plasma physics in particular, but the physics of the hot stuff in the middle of these machines. And so I thought, as a nice lead in, I'll take a few questions that pertain to that we had pre-submitted to us. So the first, I'm going to address 3 questions in one here, and these were submitted by Yuri Asnes, Mayor Bakrania, and Shiyu Na. So Yuri asks, what are the basic physics challenges in nuclear fusion nowadays? And Shiyu asks, what is the problem for the plasma to be self-sustainable? What causes energy losses, and how can we improve on that? So, and Maya asks, how do we reduce the likelihood of what we call disruptive instabilities occurring in real time? So, what are the main physics challenges that we face? Well, there are a number of physics challenges that we face, which is partly why fusion is such an interesting field, because we're designing fusion power plants right now, but we're also solving the really fundamental science and technology challenges that allow us to do that. So it's what makes it a very vibrant and interesting research field to work in. Some of the main physics challenges, and I'll focus in on some of the physics challenges that occurred inside the machine, inside the fuel, the hot fuel, that makes it challenging to get to these fusion conditions. The first thing we have to do, of course, is we have to pump heat into the fuel, which when it gets superheated, it becomes this form of matter called plasma that Chris introduced. And what we want to do is we want to pump that heat in, and we want that heat to stay in the center where it's nice and hot for as long as we can get it to stay there in order to make fusion happen, in order to make a sufficient amount of fusion happen so that we can pull out the energy from that process and we can create electricity from it. I always liken the challenge to, it's basically the same challenge as taking a cup of tea, dropping a single drop of milk in that cup of tea and trying to make that milk hold itself together as a single drop of milk in that cup of tea. Now, I assume most people here have some familiarity with milk in tea or coffee or something like that. You'll know that when you do that, it very quickly spreads out. And the same thing happens in these fusion plasmas. When you put the heat in there, it doesn't stay there. It very quickly spreads out. And it means that the amount of heat you can keep in the center reduces by the rate at which things spread away. Now, in tea, if you then take a spoon, you stir it around, you increase the rate at which it spreads out. That's because of turbulence. So turbulence is this thing that occurs everywhere in nature, where you have swirling, whirling patterns. It's what makes trees rustle. It's what makes planes bump around in the sky. And it's what mixes milk around in tea. It also happens in our machines. So turbulence in the center of our machines takes the hot stuff at the middle and mixes it with the cold stuff around the edge. And it means that it's sort of, if you've got hot stuff in the middle, cold stuff there, turbulence does that to them, starts to even them out. So it becomes harder and harder to keep the hot stuff at the center hot. And this is one really active area that we're studying right now. So lots of people look at the physics that underlies this turbulence, looks at ways of either suppressing it, understanding it, changing its nature so that either you're driving it more strongly in areas you want it to be, i.e. out at the edge of the machine, you want things to be cold, so you want turbulence there, or suppressing it where you don't want it. In the center of the machine, you want things to be hot, so you don't want as much turbulence there. Now, the brute force approach and the approach that that we see in the world at the moment with the ITER experiment is to make it bigger. Because fundamentally, if I take the hot stuff and take the cold stuff, move them further apart from one another, as they're trying to mix, that mixing becomes less and less. So it drops the hot stuff a lot less than it would do in a smaller machine, which is why making it bigger, we think will make it more effective at producing fusion energy in the center of the machine. There's also another good reason for making it bigger, which is that the amount of fusion energy you get is basically dependent on the volume of plasma, of the volume of fuel that you can keep inside the machine. But the way that you heat these machines, well, you ring it, you put all your heating mechanisms around the edge. So the amount of heat you can put into the machine is basically dependent on the surface area of the machine. So as the machine gets bigger, it starts to produce more fusion fuel in the center faster than the amount of heat it takes to get there, because the heat will vary as it gets bigger. The amount of heat you can put in goes as the length of the machine squared, but the amount of fusion you can produce goes as the length of the machine cubed. So the bigger you get, the more fusion you can produce. And that's why machines like ITER look bigger than current machines today, because we believe that's the most direct path to getting more fusion out than you put in. But there are other devices, there are other designs. So one design is the spherical tokamak, where you take something that looks like ITER, but you squish it much closer to the center. And this is the design that STEP is going to be designed upon. By squishing everything much closer to the center, you make the processes much more efficient. You make it, essentially, you make it easier to confine that fuel in the center, that hot fuel in the center. And that means that you do a better job, more efficient job of producing fusion out of the end. So that's one of the physics challenges. The other physics challenge that we really have to face is, okay, say we can get this thing running, say we can get it going and producing fusion. How do you keep it there and stop it from going off and doing something you don't want it to do? Something we call a disruption. Disruptions are events that take the plasma and make it basically wriggle away and go and hit the wall, or you lose the plasma. And these can be quite damaging. So they can put multiple tons of force, magnetic force, on the vessels. And we really need to avoid these. One of the ways that we will look to avoid them is by using clever digital techniques like machine learning and artificial intelligence to help us try and predict when one of these things is going to come along. So you can track how the plasma is doing in real time. Using machine learning and artificial intelligence, hopefully we'll be able to predict when one of these things is going to come along and take measures to avoid it, or take measures to make it slightly less impactful. One of those things is by firing a cryogenic capsule of fuel into the plasma just as it's disrupting. And by doing that, you help to dissipate some of that energy away before it goes out and hits the walls, before it does all this damage. And these are things that we're actually testing now. So we're testing these things on JET. It's called a shattered pellet injector. And we will continue to do testing on these things in the coming years. And just to come back to a couple of other points in these questions, one of the points that was raised by Yuri is, so some of these physics is really interesting. Can it be applied to other fields, i.e. astrophysics or something like that? And the answer is yes. So some of the physics that goes on in this turbulence or in these disruptions, for example, can break and reconnect magnetic field lines in the vessel. Now, this is a very similar process to what we think happens to produce solar flares on the sun. So lots about what we learn about to get fusion to work don't just have fusion specific applications, but have applications well outside our field and help our understanding of basic physics of plasmas, which is very useful because something like 97% of all matter in the known universe is actually a plasma. So we learn a lot about the universe by doing fusion experiments. Hopefully that answers those first three questions. Chris, would you like to come in with any questions of your own? Have we lost Chris?
No, I am here. My internet was going, which is almost certainly my son's fault downstairs watching Netflix. So let's all blame Joe. So let me pick up. Should we look at one of the live questions, Nick, and interleave that? So I've got far too many windows open as usual. Phil says, what level of electrical power input will ITER require when the plasma is operating? And that is extremely variable. Certainly ranging from sort of 50, 100 megawatts up to many hundreds of megawatts, depending on where you are in the pulse. It's really helped by the fact that ITER will be a superconducting machine. So ITER is a machine with superconducting coils, and that segues, I think, into a superconducting question that we've got sent earlier. So we might answer that one next. That means you don't need as much going in, but there is still quite a significant amount to keep all your systems and the heating systems up and running. It's fair to say that when you get through to power plants, we fully expect that you will largely be able to turn all the input power off. And that, coupled with superconducting coils, means your input should be massively reduced, and you should be able to have a very sort of healthy Q value where you're producing much more out than you have to put in. But this is a balance for any power plant, and certainly ITER is not a full-blown power plant and will still require quite a lot of input power. Do you want
Thanks,
to
Chris.
pick up on the superconducting question, Nick?
Yeah, I'll
Let
pick
me
up on
read
that.
it out to you, if I may. Jeremy Balshin says, how important is it to develop superconducting magnet technology to increase field strength? Will the quench become a concern for plasma stability?
Yeah, thanks. Just before I answer that, one other thing to say about the level of electrical power into ITER and other fusion power plants is that the majority of that goes into cryo systems and cooling systems. And one of the key things about a power plant that you can make smaller is these cryo systems and cooling systems are made smaller, less input power needs to go into them to drive a smaller system. So that's another advantage that's not often mentioned about these smaller power plants. So superconductors and how important is the technology, and will magnet quench, which is when you lose the superconductivity of your superconductor, be a concern? Well, most, if not all, current fusion power plant designs that are based on tokamak type technology, magnet technology, will use or assume that they will use superconducting magnets. I have seen designs where copper gets used, and you might just be on the edge of being able to use copper, but superconductors have so many useful traits that really they become absolutely cost competitive with copper, just because you can do things like use less power to drive your systems. You can run your systems for longer, so you can run your magnets for longer, if not permanently. And yes, so superconductors we think will be completely essential to most fusion power plant designs. This isn't something for the future, though. There are machines in the world that are superconducting right now. There's one in China called East. There's one which is just coming online, which is a very exciting machine in Japan called JT60 SA. And the goal of these machines is to test how you run fusion reactors with superconductors. Can you run them for a long, long time? And so far the results are yes. And can you produce the sort of performance you need to whilst maintaining the superconductivity of the magnets? And so far the answer looks to be yes. Now, certainly magnet conditions will have to be carefully monitored because you don't want any sort of unintentional loss of the magnetic field. If you do that, you will lose your hot fuel. So you'll have to shut down and restart the machine, assuming nothing worse has happened. But really, in superconducting technology, the two biggest uncertainties are, will we have to use low temperature superconductors, i.e. will we have to cool them with liquid nitrogen or liquid oxygen, or liquid helium even, to get down to superconducting temperatures which are close to absolute zero? Or will we see the emergence of what are called high temperature superconductors, which is superconductors that can go superconducting at much higher temperatures, room temperature or lower, minus 70 or 80 Kelvin up to hundreds of Kelvin. If we see those developed and coming online, they could be a real game changer for us, because they're much easier to cool, use less power input to cool them, so they're more efficient to run, or you can get, for the same power, you can get higher magnetic fields. So they might be a really important technology for fusion power plants. The other biggest unknown is, how do these superconductors behave when you fire neutrons at them? Because neutrons are going to be a big product for fusion power plants. There will be no neutron producing facility as intense as a fusion power plant until a fusion power plant comes online. So, but we can try and test these in facilities that are specially designed to do that now and before fusion power plants come online. And of course, the other thing you can do is you can take your superconductor and place shielding around it, so lead shielding, so that these neutrons are slowed down before they interact with that superconductor. So those are the sort of areas where superconducting technology needs to be looked into over the next 15, 20 years. But certainly superconductors will be very important for fusion power plants.
Great. Thank you, Nick. Should we take another live one, which is sort of linked to that? Fusion power plant's not yet practical because there is more energy put into the operation than that is extracted, and that's correct. They're not, I mean, at the minute we're experiments rather than power plants, but we certainly are in a position at the minute that where we will we do get less out from jet than we put in. And what spends the most energy and what are being done about those issues today? And I think we come back to the magnets again, that superconducting is a game changer. As Nick said, the cryogenic systems. Certainly at the minute, the heating systems, the magnets, the heating systems, the cryogenics are probably the big three that use up most of the input power. But by far the big majority is the magnets, certainly on jet. That will be dropped right down in machines that Nick's talking about, like JT60 and certainly for ITER. And then as you move to a power station, you should have much less heating power, so you certainly reduce that. And if you can bring the scale down, then you hopefully will start to reduce the cryogenics. So it's a combination of many, but the single biggest technology that will help is superconducting magnets. There's no doubt about that. So hopefully that answers that one. And then we've got another one on the chat, Nick. Maybe you could pick this one up. What are some of the key technologies which are leveraged in testing fusion? How are you building out these skills?
Oh, that's an interesting question. Yeah, and perhaps I'll take that one alongside the question from Matt about how does the UK fare in terms of labour force to be in a position to deliver fusion technology. So some of the key technologies that we need to test fusion. Well, I've already spoken about plasmas, and we study plasmas very actively in experimental machines in the UK and around the world. But there are a lot of other technologies that have to go into a fusion power plant that we don't necessarily use at the moment for our, or we use in some of our experiments, but not extensively to the, or that haven't been studied to the maturity that they need to be. Examples being robotics. Robotics, there is no way that you will want to send a human in to do any sort of replacement or servicing or inspection in a fusion power plant when it's running or after it's running. That environment is not conducive to your health. I wouldn't advise taking a stroll around a fusion power plant. So we have to use robots. And I'm sure you've all read about robotics in one form or another. Robotics is a real area of growth in the UK and worldwide at the moment. And the sort of robotics we're talking about really varies from big robots that can carry multiple tons away from the machine, can chop up and carry bits of the machine away and repair or replace it, to smaller robots that can go and do really specific jobs like crawl into a pipe and cut and weld that pipe. All of these things need to be developed, and all of these things need to be developed pretty much from prototype. And we're doing this now. So we're doing these right now in the centre that Chris mentioned called RACE. And it's not just about the jobs that robots can do, but it's about designing robots that can survive in that environment, which is not a trivial thing to do. So, so we're doing this work right now, and in doing so, we have a rather extensive PhD training program. We have an extensive network of collaborators in universities, in industry. We train apprentices, we train graduates at our centre. All of these things are to build the skills that we need for the future generation to really bring fusion into the era of deployment, and make sure that we have the skills when we need to in 2040. Now, that's not to say that that's a sort of solved problem, because to give you an example, when nuclear fission, when nuclear plants were rolled out in the 50s and 60s, the workforce was somewhere between 10 and 40,000 people that took to roll out that as an energy source. And that's the sort of workforce that we will presumably need to grow for fusion. Now, currently, our organization has 2,000 heads, more or less, in it. So we're some way off that, but what we're achieving is far surpasses, the output that we achieve far surpasses the headcount that we have. And it's down to the sort of ingenuity and innovation that we get through developing these new technologies for the first time that we can do that. And to do that, we really need to maintain our PhD training. We need to maintain our links with universities and expand our links with universities. We need to maintain and expand our graduates and our apprenticeship training. And we're doing all that. So I would put out a plea in this that if anyone is interested in fusion as a career choice, please look up some of the opportunities that we have available, because there's a lot available, and certainly building the labour force for the future is a non-trivial thing to do, but something we really have to address. But my other point is, it's a really interesting, exciting field to work in. There's almost no other field you can work in at this scale where you're marrying fundamental science and technology with real engineering for deployment. And it's, yeah, fantastic, fantastic place to work. Chris, I'll hand back to you.
Yeah, I'd add to that, Nick. Number one, you didn't think you were coming to a recruitment event, did any of you? But you were, without you realising. Number two, there is in addition a lot of work going on that we are not instigating but supporting in building a supply chain, so industry to get really involved already in building stuff for ITER. And a lot of the workforce will not just come from us at UKEA, but will come from the supply chain as well. There's private fusion companies out there now looking at things in a slightly different way. So it all builds a community and an ecosystem that will grow beyond UKEA as well, and we're very supportive of that. Okay, shall we go back to some of the pre-questions? It seems, I'm going to rely on you, Nick, to make sure we haven't missed anything. It seems the world generally should invest more in fusion. What do you think is an acceptable level of investment if we want to have a working economic reactor? I'm tempted to say, Nick, take that, but I'll start off and then Nick, you can add to it. This is a, could we have a working economic reactor in 10 or 15 years? This is an impossible question to answer because how, you know, if you just lob money at it, double, triple, quadruple the amount of worldwide money going into fusion, do you drop the timescale down that much? My gut feel is you wouldn't. I don't think you could build a working reactor in 10 years, whatever you did now. But you certainly would get there a bit quicker, and you would probably end up with a better first power station if you did put much more money in worldwide. I think, you know, people often say as a criticism, you know, ITER is $20 million or euros, whatever we want to call it, pounds, euros, dollars, they're much the same at the minute. That's an awful lot of money. It's number one spread amongst 7 worldwide partners, so Europe pays about half and the rest from all the others. Nick had a great statistic that he shared with me just the other day, which is that the big oil companies have turnovers, Nick, or I think it's turnover of around 2 trillion a year. So $2 trillion. So you can start to get some perspective. You can compare 20 billion to all sorts of other things. I'm a football fan, so compare it to the Qatar World Cup, which a conservative estimate is costing $200 billion. So one way or another, big stuff costs big money. ITER will work. I'm pretty convinced of that. When it works, it will be really seen, I think, as cheap. It will be demonstrating a technology that will be worth much more in the future, not just economically and financially, but to the planet as a whole and its health, of course. So very difficult question to answer. There is much more money coming in, and that isn't just to us, although we are getting great government support at the minute. But there's $1.8 billion worldwide now gone into private fusion companies in the UK, to a lesser extent in Europe, but certainly in the US and Canada. And it shows there's a real appetite now, and as Nick puts it, a market pull to you know, this is now the time for really to go for it with fusion. I cannot answer the question, I'm afraid, as to, you know, how much would it take to get it down to 10 or 15 years. Nick, add to that.
No, I think that's a really good summary. The only thing I'd say is that there's always a temptation with questions like this that you presuppose what an investor is willing to invest in. Now, there's almost no imaginable way that when fusion gets deployed on a wide scale, it will be deployed by the public sector. This will have to be a private sector thing. It will have to be probably major oil and gas or sovereign wealth funds coming in and building these things for mass deployment. And there's always a temptation to presuppose what level of investment, what level of risk these investors are willing to take. Now, that risk comes down through R&D. So the R&D that we're doing right now is all about solving challenges, providing solutions that takes that risk down. But at some point, investors are going to be willing to invest. And a way to view the question of how much money should be put in, well, the more money you put in, the more R&D you can do, the lower you can get that risk. So the faster investors might look to invest in these things. But there will always be a point where that ceases, because there is a certain amount of time it just takes to build these things. There is a certain amount of time it takes to build the magnets, to you know, build the buildings and things like that. So there's always going to be a limit, but and it's, you know, it's not possible. You just can't quantify it. But that's, if you were going to try and target increasing investment to do that, that's where you'd want to do it, in R&D, to try and drop that risk and bring that delivery date forward. But yeah, great question. I mean, really insightful question. That one was from Owen Lewis. I'm going to pick up 2 questions in one again. One which is in the chat, which I've just posted there so you can see it, and another one which is very similar written question, which is, with other renewable energy sources such as wind turbines expanding quickly over the next few years, how do you expect fusion energy to compete with a well-established market? And the other question that's in the chat is, let me just find it. How could we aim to make fusion energy competitive with renewables such as solar and wind, where prices have fallen significantly in the recent years? May fusion be economically viable in time to assist in the climate change crisis? Thank you. So what I'm going to say is going to sound like I'm trying to duck the question, and I'm genuinely not trying to duck the question. This is genuinely how we see fusion, is that fusion is not competitive with renewables. Renewables provide, I always think, like Chris said, I think of it in terms of market pull. And I think of it in terms of what will the energy market want in 2050? Well, the energy market is going to want sustainable energy. It's going to want carbon-free renewable energy. So renewables, there's always going to be a big pull for renewables. Renewable development is going to go up, renewable prices are going to go down. But renewables are not dependable unless you have significant, so renewables are not dependable. How do you power solar cells during the night? What do you do if the wind drops, et cetera, et cetera? So you cannot have a renewable portfolio based, an energy portfolio based solely on renewables. There's always going to be market pull for something that sits underneath that and supports renewables, that is agile and is what we call baseload. And this is where fusion fits in. Now let's think about 2050 and let's think about what the world wants that to look like. Well, the world doesn't want that to be carbon powered. So you can't have an energy source which is a producer of carbon in the atmosphere. So that's fossil fuels ruled out, unless you can get carbon capture schemes to work so effectively that you're capturing all of the carbon that the fossil fuels are producing. In which case you've got another challenge, which is, where do you store all that carbon? Because that is tons and tons and tons of carbon every year. So fossil fuels pretty much ruled out. Nuclear power, so fission power, great. Certainly that's going to play a role, but it's much less deployable. There are lots of constrictions and contingencies on where you can place a nuclear power station, and the fuel resources for nuclear power not remarkably greater than fossil fuels anyway. So as energy demand goes up, you're going to have to build more nuclear power stations, so your fuel demand goes up and your fuel resource goes down. So there is an energy pull, there is a market pull for an energy which is deployable, agile, that's fusion, zero carbon, there's no carbon produced in the fusion reaction, is safe. So fusion doesn't rely on a chain reaction event, so it's fundamentally safe. In fact, the main difficulty we have is keeping the thing going, let alone worrying about it going too fast. It produces a lot less long-lived radioactive waste than nuclear or than fission or other types of fuel. So the market pull is there, and when there's a market pull, you can expect technology to develop, and you can expect innovation cycles to develop to the point where you end up with a product that is deployable. So we don't see renewables as being a competitor. We see renewables, any energy portfolio is going to be based on renewables. Fusion is the golden egg that can sit underneath that portfolio of renewables and can power places where renewables can't match, or places where population densities are too high for renewables to be able to supply the power, or if energy storage solutions just do not come online fast enough, just do not address the sort of energy storage you need. That's where fusion sits, and fusion will be very deployable. So you don't really have many constraints about where you can put a fusion power plant. It will be safe, so you don't really need to worry about who's got a fusion power plant or where it's going to sit. And it's absolutely resource abundant, so you don't need to worry about who controls the fuel source for fusion power. So it's got all of these aspects that make it very attractive. Now, will it be there in time to solve the climate crisis? Well, I mean, I think I take that to mean, will we have mass deployable fusion by 2050? Impossible to answer, but probably by 2050, we'll be in the innovation cycle. So we'll be in the cycle. If we follow the STEP program, we'll be in the cycle where we start developing from prototypes into deployable reactors. But it's not about getting to a solution in 2050. We might well get to a solution in 2050, but that solution, if it's based on present day technology, will not be sustainable. It will be a solution, but it will not be a sustainable solution that can power humankind for millions of years to come. that's where fusion comes into the mix, because fusion has the potential to be a sustainable, and when I say sustainable, I mean long-term deployable energy strategy that can really come into the mix in the latter half of the century. So that's where fusion is so important, and that's the sort of role that we see fusion playing. Hopefully that has answered those questions.
Thank you, Nick. I'm going to pick up a couple from the pre-sent in. So let me try and do a few quick ones. Vicky Hayward, really good question. How hot does the plasma get during fusion? How do you keep the reactor tokamak cool? We've covered that already in the introduction. So typically you get to somewhere between 100 and 150 million degrees C, closer to 150 million degrees C, and you need to hold the plasma there. The how do you keep the reactor tokamak cool is a less onerous question than you might expect, because you might think, well, if that plasma touches the wall, why doesn't everything just melt? In jet, we have 1/100th of a gram of plasma. So what matters in terms of heat is the amount of stuff you've got and how hot it is. Yes, it's ridiculously hot, but the amount you've got is tiny. You will expect in a power plant to just have a gram or two at any one point in time. So when the plasma does, if it does strike the wall or touch the surfaces, it does not instantly melt everything. It will cause local damage potentially, but it doesn't melt everything. So you don't need to actively cool everything to cope with something that's 10 times hotter than the sun interacting with it. Saying that, there are cryogenic systems for keeping the magnets cold. There are cryo pumps to extract the excess heat. There are actively cooled areas, but it is not an overall issue that we have to deal with for the majority of the machine. So hopefully that helps a little bit with that. And I'll take another one just about power loads and how long are they required to start up a fusion reactor once the magnets are cooled down and charged. Will the blankets or not, in my knowledge, do they need to be preheated? If I talk about jet first of all as a copper coiled machine, we use 700-800 megawatts off the national grid. That's, depending on the time of year, that's anywhere between 1% and 2% of the UK's electricity. We don't pull it all off the grid. We have a pair of very big flywheels that store half that for us, and we pull the rest off the grid. When the weather is really cold, we're not allowed to pull it off the grid because you're all using it to heat your home. So there is an enormous amount of electrical engineering behind the scenes. For ITER, and certainly for future power stations, that input will be reduced. But it is fair to say that when you do start up, you will need significantly more as you get everything wound up to the kind of temperatures where it essentially starts to burn, as we put it, where it will keep itself hot and you can turn most of your input off. But nowhere near as much as we do need at the minute for jets. But we do not, as I understand it, need to preheat any of the major components, unless, Nick, you know more than me.
No, there are some schemes where you might look to heat up the blanket, but for not for the sort of power consumption needs. That's for whether it's useful in helping you amplify the tritium production in that blanket or not. There's not really for power production.
Okay, Nick, do you want to pick another one or two?
Yes, absolutely. Yeah, thanks, Chris. I'll go back to the chat where we've got two really interesting questions. Actually, I'm going to take one which is a bit closer to my heart because it's all about the nitty gritty of how you run these experiments, which is from an anonymous attendee. How can you tell when you have achieved fusion? Is it a given when you run a pulse? In some senses, it is a given because whenever we run any plasma experiment, a certain few of those nuclei in that plasma, in that fuel, will have a very, very high energy. It's the same, in a gas, if you've got a hot gas, most of the particles in that gas will have a certain energy, but some of them will be much, much higher energy. Some of them will be much, much lower. Same thing in a plasma. So we we get some fusion. And indeed, one of the ways that we heat our experiments is we fire in a beam of neutral fuel particles that come in, collide with things in the plasma. And when they do so, they can induce fusion as well. Of course, you don't produce enough energy out of that to even get anywhere near the inputs that you're putting in there. But we do fusion. So in some senses, it is taken as a given in these things. But how do you tell if you're getting proper fusion power? How do you measure the fusion power? Well, the way we do it is actually reasonably simple. There are a few. What you want to detect is the neutron. So the fusion reaction that we use is deuterium and tritium. Deuterium is 1 proton and 2 neutrons. Tritium, 1 proton and 1 neutron. Tritium is 1 proton, 2 neutrons. They become helium, which is 2 protons, 2 neutrons, and a lonely neutron. And it's that lonely neutron that can fly out of the machine and carries 4/5 of all of the energy from that reaction with it. So if we can, we know what the fusion reaction actually looks like really quite well. We've known about fusion since the 1920s. So the actual fusion part of it is pretty nailed on now. So we know what energy that neutron has. So if we can measure the number of neutrons that come out, multiply that by the energy of a neutron, you can figure out how much fusion power you're producing. And there are a few different ways you can measure neutrons. You can do it in what's called a fission chamber, where you have a small amount of nuclear material in that chamber. When neutrons come in, they hit it, they cause a fissile decay, and you can measure the output of that decay. That tells you if you've got a neutron. There are other ways of measuring neutrons as well. And we have on one of our machines, we've got a very clever thing called a neutron camera, where a neutron comes out and hits a film. And so you can tell not just how many neutrons have hit it, but where they've hit it. And you can measure that at one point, and then you can then make an assumption on, if you say, okay, I've got this many neutrons within this gap of space, how much space do I fill with the whole experiment? And you can figure out what sort of power you produce. So actually, it's reasonably simple. I say simple. The people that operate these devices would tell me it's not simple, but it's reasonably straightforward to get that information. Diagnosing these machines is such an interesting art form, and it really is a bit of black magic sometimes on how you tell I mean, just think about it. How do you tell if something is burning at 150 million degrees? You can't just stick a thermometer in there. So there's a lot that goes into diagnosing these plasmas. And I could talk for a long time about it. I won't go too heavily more. But, yes, so that's how we know fusion happens. Actually, just before I hand back over to Chris, one of my favorite ways actually of knowing when fusion happens. So we put cameras all over our machines so we can see what's going on. These cameras measure a certain type of light, which is the same sort of light that if you're looking at the surface of the sun, you put a filter over your telescope. We have the same sort of filter in these cameras. So you essentially look at the surface of the plasma. Now, if you see one of these videos from a fusion plasma, it looks kind of speckled and it looks like something's going wrong with the camera. Those speckles are actually neutrons born out of fusion coming and hitting the camera sensor. So you can't really measure them, but you can definitely tell that fusion is happening just because it looks like your camera's broken. So that's my sort of informal favorite way of telling when fusion is going on. I'll hand back to Chris.
Far more fusion than you ever think is happening. There's a really good question from Hamid in the pre-assigned ones, the pre-sent in ones. Why do UKA not support any other project except tokamaks? In other words, leading on to ITER, and indeed Masters is still a tokamak, but a more compact one. I think that the very quick answer, but then there'll be a longer one, I'm afraid, is the fact that we have our work cut out just in terms of tokamaks, and traditionally that's what we've grown to look at. But there are, within the magnetic confinement fusion community, and that is devices like tokamaks, there are others. Tokamak, I think it's fair to say, is the most advanced in its understanding and planning for what a power plant looks like, as we've already described with demo step, etc. But there are devices called stellarators, big one in Germany being looked at. And we indeed did look at stellarators in the past in the authority, maybe 30 or 40 years ago. And we also looked at things called reverse field pinches. Way outside of magnetic confinement fusion, there is a whole nother branch called inertial confinement fusion, which is very different in its concept. Rather than a relatively small in mass, large plasma heated and held relatively continuously in the magnetic clutches of your tokamak, with inertial confinement, you have a very small solid pellet of fuel that you implode with laser beams or X-rays from laser beams. And the implosion will cause a very quick blast of fusion, or in principle can, and they've demonstrated a little bit of this in devices. And you would then repeat that. So it's not a continuous process, but one where you constantly repeat the implosion and keep fusion running. That's what potentially an ICF power plant might look like. We have never looked at that at the authority, but there is some laser research going on in the UK, and there are devices certainly in the US and Japan that are looking much more carefully at that. look at all of them, is we are part of a wider UK and certainly part of a wider European and international programme, very collaborative. It's not in our interest to therefore go and study stuff that is being looked at elsewhere. We are part, and MAST is part of a European programme that very carefully has a compact device like MAST in it, JET and more conventional machines, and the Stellarator. And at some point, Europe has to decide which of those it continues to pursue. But at the minute, all are being looked at, and they're learning off each other. So there's no real interest in us. We've got our work cut out with just Tokamaks, but there's no real interest for us as the authority to really look beyond that into other schemes.
Thanks, Chris. We're nearly out of time. We've got 5 more minutes left. So if you've got any other burning questions, get them in the Q&A chat. I'm going to take, I think, what is a brilliant question and a really fun one to be able to answer. And I think both myself and Chris should get a chance at answering this because it's a great question. Tobias has asked, what has been the most important development for Fusion in the last decade? I'm going to cheat a little bit with this. So I'm going to give you what I think is the most important development for Fusion in the last decade. And I'm going to tell you what I think will be one of, if not the most important development for Fusion in the next decade as well. So in the last decade, and this is really on the verge of the last decade, so back in 2011, the biggest machine in the world is JET. The hottest machine in the world is JET, and JET holds Fusion power records. So JET is this machine at Culham site. It's our site, UKA site in South Oxfordshire. We run it on behalf of the European Commission. In 2011, a major refurbishment of the inside of JET happened. So JET originally, if you looked inside, it would look mostly black or sort of a tarnished grayish color because most of the inside of JET was made of carbon. Now, carbon is great because if you want something to deal with high heat, and you have a lot of heat in a fusion reactor, if you want something to deal with high heat, you use carbon because carbon can handle heat and it doesn't melt. It gives itself away atom by atom, it sublimes, but it doesn't melt. However, in our reactors, we have 2 isotopes of hydrogen, and particularly tritium is very rare, very hard to produce, and it's radioactive. So you have to be able to control where tritium goes in your system. Now, carbon and hydrogen really like each other. They really like to bond and they form hydrocarbons. So you start putting hydrogen down on a carbon surface and you're going to lose a lot of that hydrogen or tritium into that carbon surface. So it's not a good choice if you want to do a fusion, if you want to run a fusion power plant where you need as much tritium in your system as you can get, not losing it all into the wall. So you can't use carbon. And in 2011, JET upgraded all of its inside material to be metallic. So the walls of JET are now beryllium, and the diverter, the place where we handle all the really high heats, is made of tungsten. This wasn't an arbitrary choice. The reason that we chose these materials was because ITER will use exactly that mix of materials when it comes online. And I think that, and this for me is the biggest development that's been made over the last decade. It's important on so many levels. First off, we've managed to test almost all of the physics that we used to know how to run in a carbon machine now in this metal wall, which means that when ITER comes online, we have much more confidence in the way that we're going to operate it, meaning that we can have a running start at ITER rather than learning how to do everything from scratch. Secondly, and this is an example of where this has had a real impact, we've managed to test things like a tungsten diverter, which is this, can we deal with this really high heat flux using tungsten? And we've managed to test it enough that actually the world is confident enough in using a tungsten diverter that ITER will no longer need to start with carbon. ITER can move straight into starting metallic, which saves a lot of money because you don't need to replace that component anymore. But more importantly, we've learned about the physics that goes into that. So we can be reasonably assured now that if the physics holds true, which we think it will, that we have a good basis for being able to operate ITER. So in my opinion, that is the most important development that's been made in the last decade. Now, I said I was going to cheat and tell you what I think will be the most important development made in the next decade. And hopefully it's be a development that's made much closer than in 10 years' time, maybe this year, maybe in the next few years. We'll be demonstrating in a machine, in JET, in this ITER-like wall, that we can meet and extend the record-breaking fusion performance that JET already holds. So JET holds the world record for fusion. JET produced 16 megawatts of fusion power back in 1997, which is about the same as 10 wind turbines. So, you know, not insignificant amounts of power. Power a small village. JET produced 16 megawatts. Unfortunately, JET took 25 megawatts to get there, so it's not break even. But what we need to do now is show that we can get to that same level of performance using a metal wall. And not just that we can get to that level of performance, but we can extend that duration so that we can do that controllably and understand how we keep that optimum performance going for as long as possible. When we can do that, we've really shown that we understand this machine as well as we can, and we can operate it at peak performance, which puts us in a really good position when ITER comes online to make ITER a real success. So that's my opinion. And I say that with a heavy heart because the machine I love and that I've worked on for most of my career is Mast Upgrade, which is going to do some other really interesting stuff in the next decade as well. Chris, I don't know if you want to come in on your...
Yeah, I will. And you actually stole mine for the last decade, which was putting the ITER-like wall inside JET, which I think we both agree. I'm going to be a bit more generic. I've worked at Culham 31 years as a physicist and in communications for 20 odd. It's the realization in the last few years, and with the new technology facilities we've mentioned today, RACE and our materials research facility, but I think a real recognition that what really matters now is not so much the fundamental physics of the plasma, but the engineering around it, and that we need to gear ourselves up to test that. In other words, we all know around here that fusion will work. In fact, indeed, it does work in JET at a very low level, and we've demonstrated significant levels, as Nick just said. What you need to do is do it economically, and that economically is an incredibly loaded word that requires you to run for very long periods of time, at a time, to have a total lifetime of 40, 50 years, to make electricity at a price we want to pay, to produce the base load, to underpin renewables. That requires you to get the right materials, the right robotics. All of the technologies and the engineering are what's really come to the fore now. And that flip, which I've seen happen gradually over a few years, gives me real excitement as we look forward to a power plant, that we really are now focused on that final device. We're decades away from building it. But now we know the challenges in front of us, and we're certainly, as the authority working with others, we're really facing up to that. So I think that would be my slightly more generic answer. And in terms of the one coming up, I would allude to the one that Nick just mentioned. In the next year or so, Mast Upgrade will demonstrate a new diverter design. The tungsten standard diverter in JET, even with tungsten, will really wear out quite quickly in a future power station. A new, more efficient diverter with much lower heat loads called the SuperX diverter in Mast should start to show results inside the next 12 months that show much lower power loadings and potentially give a route to a more effective way of exhausting heat out. And I really think that would be a real game changer.
Thanks, Chris. So I think we're pretty much out of time and need to start drawing this to a close. There's one question in the pre-submitted questions that we haven't touched on. And if I may, Chris, I thought I'd just very quickly end with that one with a sort of very quick answer. Not in things like this, it's often quite fun to finish on a grand question like the one we just had. But I really like this question because this is what fusion research is all about, is can we be speculative? Can we do something that is going to make a game-changing approach? And the question asked is by Matt Mosley: can we use graphene in the construction process, given its ever-growing applications, including its electrical conductivity, its heat resistance? Can it be useful? Now, I don't have a good answer for you, Matt, because of course the answer is we don't know. But it's definitely somewhere. Graphene, like superconductors 20 years ago. Graphene is an absolute super material now. And what I will say is that fusion devices are complex. They are extraordinarily complicated things. In ITER, there is over 1 million different components that go into ITER to make it work. And these all have to be precision engineered and have to work together. It's almost unreasonable to expect graphene not to play a role somewhere in there, given that so many of the components deal with electrical circuitry or heat circuitry. So I'm sure you'd see graphene in there, but I'm sorry, Matt, I can't give you a better answer than that. I can't tell you that we're going to make fusion reactors out of graphene, but I really like that question as a good place to end on, because that's what research is all about, is looking for the next big idea, and we're definitely working on that ourselves. So unless there's anything, any other questions you'd like to come to, Chris, I would suggest.
Yeah,
sorry,
there's just one very quickly. If we just want to finish off from Phil in the live chat, power magnification factors in the lithium blanket. It isn't really power magnification in the lithium blanket you need to think about. The lithium blanket is there to absorb the neutrons, heat up, and we expect it to heat to several hundred degrees, maybe 500-600 degrees, and that then feed into some kind of steam generator circuit to generate electricity. Always ironic to me that we'll use that what seems like old technology to actually turn a turbine and make electricity. But it also reacts the neutrons with the lithium to make tritium. And there is a magnification there because we won't expect every neutron to hit the blanket. So we will probably have a 20-30% breeding ratio where we will need to make more lithium than the neutrons coming in, if that makes sense. And that requires a mix of lithium 6 and 7 that we won't go into now. So hopefully that helps answer that. I didn't want Phil to sit there for the last hour and think his question was the only one not to be answered. So hopefully that's helped answer that one. And then I think we are pretty much done, Nick.
Thanks, Chris. Sorry, Phil, I did miss that myself. So thank you everybody for joining us. We've had that really fantastic questions. I'm sure Chris would agree with me that, very stimulating questions. And if there are any questions that you've got that didn't get answered or you didn't feel like you wanted to ask now, please feel free to reach out. You'll be able to email the comms team or find us on LinkedIn or any of our social media and reach out. And keep following Fusion, because this next decade is going to be one of the most extraordinary decades ever in Fusion. We've got JET doing things, we've got Master Upgrade doing things, we've got Fusion design programs going into their next stages, and ITER is going to come online. So keep following Fusion. It's an exciting world to be involved with, and come and share the journey with us. So thank you very much, everyone. And I'll let Chris say a couple of words before we end the session.
No, thank you. Just to reiterate that, it is a really exciting time, and keep an eye on us. Thank you very much for coming today. The questions have been really good. You always wonder what questions you're going to get, but they've been really insightful, really challenging. And me and Nick, as you can tell, love this kind of thing. So we'll try and do this one again. Okay. Thanks, everybody. Have a good rest of your day.